Year 9, Investigating Quadratic Graphs. In your last lesson, you made use of Desmos to investigate the shapes of quadratic graphs. We're now going to look at some of your findings in closer detail. Please make sure you have the original sheet, which was a PDF, out in front of you so you can recall the questions that you were asked and the graphs that you were asked to investigate. And please make sure you have your notes at hand as well that you made from the last lesson. It's also useful for you to have a browser window with Desmos open so you can test out a few ideas, and at the end there'll be something for you to explore using Desmos again. So I have sketched here the first 5 graphs that you are asked to draw, and the colours match the colours at the side in the key here so that you can see. So in red we have our original graph, y equals x squared. And then we have slight adjustments of this graph, as you can see. So let's take the black graph over here, y equals x squared minus 2, as an example. And I asked you to make sure you made a note of the y-intercept of each of these new graphs. So here, this has a y-intercept of 0, -2. What about this blue graph over here? This is the graph of y equals x squared plus 3, and can you see what its y-intercept is? 0, 3. So hopefully you noticed that when you add or subtract a single number at the end of the graph of y equals x squared, this results in the graph moving up or down vertically on the y-axis. There's a mathematical word for that. It's called translating, when you move something. So we could say the graph has been translated by however many units. So this graph, for instance, here, y equals x squared plus 2, if you look at it, you can see that the original red graph has been shifted 2 units up the y-axis, so the y-intercept is now 0, 2. So adding a single number to the y equals x squared graph's equation results in the graph moving vertically up or down by this many units, and we call this a translation. And if you can think back to when you looked at the transformations topics in year 7 and year 8, you will remember hopefully a little bit about translations and a little bit about translation vectors, and this is something you will study in much greater detail in year 11 as part of your GCSE. So my next pair of graphs, in blue we have y equals x squared, and then in green we have y equals -x squared, and you were asked to have a think about the effect of the negative sign and how that changed the graph. Now, some of you may have used words to describe it, like flip, and that's one way in which you can describe the movement. A more mathematical way is to say that a reflection has taken place. Now, can you see the mirror line? It's here, it's the x-axis. So imagine reflecting that blue graph in the x-axis, you get the green graph, or vice versa. Reflect the green graph in the mirror line, the x-axis, and you will produce the blue graph. So here we have a reflection in the x-axis. So the negative sign results in a reflection of y equals x squared in the x-axis, which is the mirror line. Now here we have quite a large number of graphs plotted on one set of axes, so make sure you can tell them apart. This red graph here is y equals 0.5 x squared, and we can also see the blue graph, which is y equals x squared, and then I'm just going to label the black graph here, y equals 3x squared. We'll focus on these 3 to begin with. So you were asked to explore, using Desmos, the effect of changing the number here in front of x squared. Now, in the first graph, y equals x squared, you could describe that as y equals 1x squared, except of course we don't write that 1 as a multiplier in algebraic notation. Now, what happens as you make that number larger? Well, you can see that here in the graphs y equals 2x squared and y equals 3x squared, the graphs become steeper, they stretch, and that is actually a correct piece of mathematical terminology here. They are stretched by factors of 2 and 3. Now, when you make the number in front of x squared lower, like that, the graph becomes less steep. and that's because it's stretching with a fractional scale factor, a scale factor of a half. Now, some of you may have noticed a few nice points about the coordinates here. For instance, if we pick this coordinate here on the graph of y equals x squared, you can see it's 2, 4, and it matches this coordinate here, which is 2, 2. Now look at the y coordinate. Can you see it's multiplied by a half? The x coordinates stayed the same, but the y coordinates change, and that's what creates the effect of the graph looking steeper or less steep. You're stretching the y coordinates. Now, there is a mathematical word for the number in front of x squared, or the number in front of any algebraic term, and that's called the coefficient. It's not a term you really need to worry about for the purposes of Year 9 maths. It's something in A-level maths that we would talk about a lot, but just as a point of interest, we call the number in front of the algebraic term the coefficient. So what we might call the multiplier, perhaps, is also called the coefficient. So as the coefficient becomes larger, the graph becomes steeper. As the coefficient becomes less, the graph becomes less steep. Now, in the blue and the green graph here, we have y equals negative 2x squared and y equals negative 3x squared. Now, hopefully you can see a combination of the effects we've looked at here and the effect of the negative sign as well. So, for instance, the graph of y equals 2x squared, which you can just about see in purple here, and the graph of y equals negative 2x squared essentially have the same level of steepness, but they're reflections of each other in the x-axis. So, important to realise that the coefficient, the number in front of the x squared, dictates how steep the graph is, and if there is a negative sign, this just results in a reflection. So now let's look at the next part of the investigation. So we have a series of graphs here stacked together. Let's add in a little bit of labelling. So in blue we have y equals x squared. Now in purple, you can just about see that, we have y equals x squared minus x. The black graph is y equals x squared minus 2x, and the red graph y equals x squared minus 3x. Now, what was the effect here of having an x term included? Well, it certainly seems like this results in the graph moving perhaps across and potentially down as well, which is another type of translation where something moves. Now, it's actually really difficult to see this because we have a large number of graphs in a small space, and if you want to look at this more carefully, open up Desmos and have another look, the graphs essentially all have the same degree of steepness. They're just in slightly different positions, so it's difficult to actually see that their level of steepness is the same. Imagine you pick up that blue graph and you literally move it across and down. You don't change its steepness, you just change its position. As part of your investigation, I also asked you to look carefully at where graphs cross the x and y axis. Now, in each of these cases, the graphs cross the y-axis at 0 at the origin. Now, why is that? Well, think back to the earlier part of the work. We haven't got a number, a single number at the end of each equation, so effectively it's plus 0 in all of these cases, which is why the graphs cross the y-axis at 0. Now, let's look at where the graphs cross the x-axis. So hopefully you've labelled this on your diagrams, but here, for instance, this graph crosses the x-axis at 0, 3. All of these graphs cross the x-axis at 0, 0 as well. The black graph crosses the x-axis at 2, 0. That purple graph at 1, 0, and of course the blue graph at 0, 0. Now, I suggested as a bit of a sort of extension activity that you could see what happens when you try factorizing these graph equations. So y equals x squared minus 3x. If you factorize this, you get x minus 3. Now, it's interesting then that the graph crosses the x-axis at 3. Now, this one over here, if you factorize it, you get x minus 2, and it crosses the x-axis at 2. And this pattern repeats in all of the examples. Here's the last one here. Y equals x squared minus x, or y equals x bracket x minus 1, and the graph crosses the x-axis at 1. And all the graphs also cross at 0 as well. This is something we will explore in a little bit more detail. So a little bit later on. So for the moment, we can say that adding an x term, or subtracting an x term, I suppose in this case, results in the graph moving. And by all accounts, the graphs appear to move to the right and down. So including a negative bx term, so for instance, here we have negative x, negative 1x, negative 2x, negative 3x, results in the graph moving across and down. So it's another type of translation that's occurring here. Now, this time we have something very similar, but instead of subtracting the x term, we're adding the x term. And as you can see, looking at the graphs, so here's y equals x squared plus 3x, here's y equals x squared plus 2x, etc., that the graphs move, but this time they appear to move to the left and down. So we have another type of translation. Now, notice again, if you factorize the equation of the graph, you might notice that the graph crosses the x-axis over here at the point negative 3, 0. And this must have something to do with the equation of the graph, which is something we will look at a little bit later on. So again, we have another translation. So it's clear that if you start with y equals x squared, your very standard parabola, and you include either a plus x or a minus x type term, then that results in the graph being translated left or right and then down. So what happens when we tie some of these ideas together? So have a look at the blue graph, which is our starting point, y equals x squared. And I want you to have a look at this green graph here, which is y equals x squared plus 5x plus 6. So this graph has an x term and a constant, a numerical term at the end. Now look at its y-intercept. We're looking at the green graph, remember. It crosses the y-axis at 0, 6. And you may have noticed it crosses the x-axis at these points here. This one, negative 2, 0, and this one, negative 3, 0. Now let's focus on the green graph for a moment. So the graph y equals x squared plus 5x plus 6. And we're going to think about why it is that this number here tells us where the graph crosses the y-axis, because you can see it on the purple graph as well. So that's this graph here. There's a plus 5 at the end, and you can just about see that the purple graph there crosses the y-axis at 0, 5, something we noticed earlier on. So why is this? Well, when a graph, any kind of graph, crosses the y-axis, imagine a graph crosses the y-axis all the way down here. It can be any shape it wants to. Look at that red line I've just drawn. Imagine that's a graph crossing the y-axis. What is the x-coordinate at that moment in time? So the x-coordinate will always be 0 when a graph crosses the y-axis. So if we substitute in x equals 0 into this equation for y, we get y equals 0 squared plus 5 times 0 plus 6, which of course is just 6, which is the number at the end. And that's why whenever you want to find out where a graph crosses the y-axis, you're just looking at the constant term at the end of its equation, because whenever you substitute in x equals 0, any terms that involve x will become 0 themselves. Now, what requires a little bit more thought is understanding where a graph crosses the x-axis. Now, at this point, we are dipping into maths that largely is covered much more at GCSE level than in year 9. So we're really only going to give this a very brief introduction, and it is something you will see in much more detail later on. So this is just a taster, an introduction. So I want you to consider the graph of y equals x squared plus 5x plus 6. Now, when this graph crosses the x-axis, its y-coordinates will be 0. Again, look at this red curve I'm going to draw here. as it crosses the x-axis, can you see its y-coordinate will always be 0? And that's true of any graph. Whenever a graph crosses the x-axis, its y-coordinates will be 0. So if we want to find out where a graph crosses the x-axis, we simply set the y-coordinate equal to 0. And we end up with 0 equals x squared plus 5x plus 6. Now, one thing you have learnt is that this, on the right-hand side, is what you would describe as a quadratic. And you know how to factorize a quadratic. So let's do that. So if we factorize our quadratic, we will have two brackets, x and x at the start, and our two numbers need to multiply together to make 6 and add together to make 5. So it's a very easy quadratic, x plus 2, x plus 3 in our brackets here. Now, this is more than the quadratic expressions that you have factorized previously. This is a quadratic equation because it's equal to 0. That's what makes it an equation. Now, think about how this can work. If you have a product, and that's what we have here, we have a product of x plus 2 and x plus 3. We have two brackets which are being multiplied together, and this results in a value of 0. Now, the only way that you can multiply two things together and get an answer of 0 is if one of the two things is actually equal to 0. So either x plus 2 has got to equal 0, or the alternative is that the other bracket, x plus 3, has got to equal 0. Let's solve these little equations. What do we get if x plus 2 equals 0? X equals negative 2. What do we get if x plus 3 equals 0? We get x equals negative 3. Now, where did any of this come from? All of this came from us setting the y-coordinate equal to 0 and finding out what the x-coordinates would be as a result. And this gives us a pair of coordinates, negative 2, 0, negative 3, 0, which are indeed where this graph crosses the x-axis. Go back and have a look. There they are. Now, as I said, this is something that you're going to study in much more detail later on at GCSE level, but it's interesting for us to have a little look at this now. So let's see if we can do something similar with this graph here. So the purple graph is the graph of y equals x squared minus 6x plus 5. Now, let's make the y-coordinate equal to 0. So we get 0 equals x squared minus 6x plus 5. Now, we can factorize this quadratic equation on the right-hand side. X minus 5, x minus 1. And then again, think about what we have. We are multiplying two things together. It doesn't matter that they're algebraic, it doesn't matter that they involve brackets. We are multiplying this and this together, and it's resulting in an answer of 0. Now, the only way that that can happen is if either one of the brackets equals 0. So either x minus 1 equals 0, which of course gives us x equals 1, or the alternative is that the other bracket, x minus 5 equals 0, which gives us x equals 5. Now, this gives us a pair of coordinates, 1, 0, and another pair of coordinates, 5, 0, and have a look. This matches perfectly with where this graph crosses the x-axis. So your key takeaway points from here are, if you want to find out where something crosses the y-axis, substitute in x equals 0. If you want to find out where something crosses the x-axis, substitute in y is 0. And in both cases, you then need to find the other coordinate. We'll perhaps write a note down about that a little bit later on. So now, let's see if everything we've looked at applies to another example. So here is y equals x squared, and in black, can you see my quadratic graph here? Y equals x squared plus 3x minus 4. So remember what we said. When a graph crosses the x-axis, its y-coordinate is 0, and when a graph crosses the y-axis, its x-coordinate is 0. So when a graph crosses the y-axis, its x-coordinate is 0. So let's take the equation of this graph, y equals x squared plus 3x minus 4, and of course, if we make its x-coordinate equal to 0, y then equals 0 squared plus 3 times 0 minus 4, we get y equals negative 4. So we get a coordinate 0, negative 4, and look here, the graph crosses the y-axis at 0, negative 4. Now, let's think about where a graph crosses the x-axis. When anything crosses the x-axis, at the instant it crosses the x-axis, it will have a y-coordinate of 0. So let's see what happens when we make y equal to 0. So again, I'm going to take the equation of the curve, y equals x squared plus 3x minus 4, and this time I'm going to make the y-coordinate equal to 0. So I get 0 equals x squared plus 3x minus 4. And here we have, again, a quadratic equation. Now, at GCSE, you will spend a lot of time looking at quadratic equations in depth. You will look at solving quadratic equations in detail. You will look at a variety of different quadratic equations. So all we're doing is just giving you a little taster, a little introduction into these at the moment. So please don't worry about this too much because it's something you will spend a lot more time on later on in year 10. So factorize on the right-hand side because that's one of the main ways in which you can solve a quadratic equation. And this will give us x plus 4, x minus 1. So a good opportunity to practice our factorization skills. So what did we see last time? We talked about the fact that you are making a product. It's a product of x minus 1, and we have a product of x plus 4. Now this product gives us a result of 0. Now the only way that two things can multiply together to give you an answer of 0, to give you a product of 0, is if one of those two things is actually equal to 0. Okay, think about it. How do you multiply two things together and get an answer of 0? One of the two things must be 0. So either x plus 4 must equal 0, or the alternative is that x minus 1 must equal 0. Now, what does this then tell us about the value of x in these two situations? Well, if x plus 4 equals 0, x equals negative 4. If x minus 1 equals 0, then what does that tell us? It tells us that x has got to equal 1. So remember where all this came from. It started from setting the y-coordinate equal to 0. And that results in two possible options for x. It results in a coordinate which is negative 4, 0, and another coordinate which is 1, 0. Now look at the graph. This matches perfectly with what we can see because the graph crosses the x-axis in two places, one at 1, 0 and another at negative 4, 0. So that's how the equation of a quadratic function relates to the different features of that quadratic function as a graph. So now let's move on to the next pair of graphs that you were asked to sketch. So these are quite interesting. Again, let's have a look. You can see if we substitute in x equals 0 into this equation, we would end up with an answer of y equals 4. So again, this value at the end giving us our y-intercept. So just confirming everything we've seen. Now these graphs are interesting because they don't cross the x-axis, but they touch the x-axis at single points. Now why is that? Well, let's take this graph here, y equals x squared plus 4x plus 4. Now, remember what I've been saying, if you want to know where something crosses the x-axis, you make its y-coordinate equal to 0. So 0 equals x squared plus 4x plus 4. Now, here we are. Here's a quadratic equation again. And let's factorize this quadratic equation. So we get x plus 2 x plus 2. So we get a repeated pair of brackets. Now, what does that mean when we try and solve this? So remember what we've been talking about with the solving of quadratic equations. And again, I repeat, this is something you will study in much more detail, in full detail at GCSE. So this is just a little taster of that, some of these concepts. So you have a product of x plus 2 and x plus 2, and they're multiplying together to make 0, which means one or the other must equal 0. But in this case, they're both the same. So whereas in the previous examples, we had two little mini equations to solve, all we have here is one equation to solve x plus 2 equals 0, so the graph only intersects with the x-axis at one point, -2, 0, which we can see over here. So the overall effect is that the blue graph looks like it's just been moved to the left. It doesn't appear to have moved up or down, it's just shifted or translated to the left by 2 units. Now, does something similar happen with the green graph over here? Well, let's take a look at its equation. Y equals x squared minus 2x plus 1. And again, look at its y-intercept there. We can see it crosses the y-axis at 0, 1. What happens if we make y equal to 0? So that then gives me 0 equals x squared minus 2x plus 1. Now, can you factorize this quadratic here? Maybe pause the video and have a go at doing it. So our brackets must begin with x and x. They've got to multiply, we've got to find two numbers that multiply together to give us 1, add together to give us -2, so it's -1, -1. And again, we have the same situation where we've got a repeated bracket. So that means when we're looking for what must be 0, there is only one option because the brackets are identical, and that is that x minus 1 equals 0, so x equals 1. So we now have a pair of coordinates, 1, 0, which tell us where the graph intersects the x-axis, and there it is. There's the point itself, 1, 0. And again, the green graph looks like the blue graph has literally been moved to the right by 1 unit, or a translation of 1 unit. So the last graph that you were asked to draw was this purple one here, the graph of y equals x squared plus 2x plus 4. Now, if you were asked to describe in words what's happened to the blue graph to turn it into the purple graph as a result of this part here, which has been added in, well, it certainly looks like the graph has been moved up and also perhaps slightly to the left to make it work. Again, it's difficult to see this with the perspective that you're given from this screenshot, but there has been no change in the steepness of the graph because we haven't multiplied x squared by a new number. Both of these are 1x squared, and it's a number in front of the x squared. Remember that word coefficient that determines the steepness of the graph. When you add other parts, sort of add a 2x or add a 4 or whatever, that just moves the graph from one position to another. It doesn't alter the steepness. Now, this graph crosses the y-axis at 4, and you can see that from the equation as well. And interestingly, it doesn't cross the x-axis at all. Now, something that you might find interesting is if you actually had a go at factorising x squared plus 2x plus 4, you would find that you wouldn't be able to factorise it. Not all quadratics can actually be factorised, and not all quadratic equations have answers. And this in particular, if we try to solve this quadratic equation, it doesn't actually have any answers. There are no values of x that you can input into this to get a value of 0, and that's why this graph doesn't cross the x-axis. Now, again, I want to reassure you, this is something that you're going to study in full detail at GCSE level. So again, if you're feeling not as confident as you'd like about some of this content, please don't worry. Perhaps go back and re-watch parts of the video again, but please rest assured you will see this in much more detail again at GCSE. So let's have a little summary of what we've discussed. So the graph of a quadratic function can be expressed in general in this format here. Y equals ax squared plus bx plus c. A, b and c are numbers. And your task in your previous lesson was to identify what the effects of changing the values of A, B and C were on the shape of the graph. Now, there's a nice feature that you may have used on Desmos. You may not have had a chance to explore this last lesson, so I recommend you open a window and have a go at this now. If you input the equation of a quadratic like this, so as I've done here in the screenshot, then the option comes up to use a slider for A, B and C. And what you can do is move that slider along to change the values of A, B and C, and then see how this affects the shape of the graph, which is a really interesting way of doing it. You might perhaps leave A at a particular value, leave B at a particular value, then change the value of C and see what happens. Then fix one of the others and again change one of the others, and then that will hopefully consolidate some of the things that we have talked about today. So the last task that you were asked to complete in your last lesson was to try and jot down some notes about how changing the values of A, B and C affect the shape of the graph. So let's perhaps summarise some of the things that we have talked about here. How did the value of A affect the shape of the graph? So changing the value of A affects the steepness of the graph. You can see, and again, do use Desmos to have another look at this if needed. Let's imagine this is my pair of axes. If I have a steeper value of A, my graph will perhaps look a little bit more like that, compared to if I have a less steep value of A, when it will look a little bit less steep. So the larger the value of A, we end up with a steeper curve. And that's described as a stretch, so it stretches upwards. Now, what about the value of B? Well, the value of B, changing the value of B, results in the graph either moving left or right, and the value of B will dictate how far left or right it moves. And this value C here, of course, tells you where the graph crosses the y-axis. So changing the value of C results in a movement either upwards or downwards, so a vertical movement. Now, what's interesting is that all three of these values then work together in affecting the overall shape of the graph. Now, do go back and use the Desmos software again, use the general form of the equation of a curve here, alter the values of A, B and C, and justify to yourself that you can see how changing the values of A, B and C affect the shape of the graph, and how those values of A, B and C interact together to affect the shape of the curve. Now, all of this will set you up very nicely for work that you will be covering later on at GCSE level.